Okay, so let's look at the fourth one here. The fourth one says three forces, force 1, force 2, and force 3 are acting upon an object. The x and y components are shown. Complete the following blank statements by placing basically a greater than sign, a less than sign, or an equal to symbol in the spaces provided. Okay, so we have three forces here, and these three forces here are shown in black, and they're acting on our object. Okay, and it turns out that this object is in static equilibrium, meaning the system is not accelerating. So this object is not undergoing any sort of acceleration. So guys, I want you guys to remember what I said in a previous video. It is always true that anytime our system is not accelerating, that all of our forces, all the forces acting in the x direction, you add up all those forces, they equal to 0. And it is also true that the sum of all of your forces acting in the y direction, and when you add up all these forces, all these forces are also equal to 0. And this is true for a situation that is in static equilibrium. And we are assuming here this situation is a static equilibrium. Okay, so guys, let us begin by looking at these forces. So notice force 1 and force 2 are acting at an angle here. So I'm kind of, bold this a little bit more for you guys. So force 1 is pulling like this. It's pulling up at the same time as pulling to the left. Whereas force 2 is pulling like this. It's pulling to the right at the same time that it's pulling up. Okay, so remember, anytime we have a force acting in the acting in both directions, meaning it's acting in both y and x, is pulling up at the same time as pulling to the left, we can split this force up into its x and y components. And that's what they did here in blue. They split this single force up into its x component, and they split this force up into its y component. So the x component looks something like this. So the force 1 acting in the x direction looks something like that. Remember, it's pulling to the right at the same time that it's pulling up. So it's also acting in the y direction like that. Okay. And the same thing for this one right here, force 2. Force 2 is pulling in the x direction. Pulling in the x direction. So force acting in the x direction at the exact same time as acting in the y direction. Again, all we're doing, we're just taking these forces in black here, and we're splitting this force vector up into its x and y components. We're figuring out how much acts in x and how much acts in y. Okay, assuming there were numbers there, we could actually do that using trigonometry. But for now, we're not really concerned with any trigonometric functions. We just want to answer these questions. If this system is in static equilibrium, let me ask you guys a question. How does the force 1 pulling in the x direction compare to force 2 pulling in the x direction? Well, remember what I said, anytime we're in static equilibrium, the sum of the forces in x must be equal to 0. So whatever this force is right here, so I'm just going to throw out a number. Let's just say, let's just say this number here, this force, let's just say it's -6 newtons pulling in that direction. Well, if we're in static equilibrium, if this force is say -6 newtons, that means this other force right here would have to be +6 newtons, right? Because when you add up those forces, you have to get a resultant force that's equal to 0. So that means the magnitude of this force here is equal to the magnitude of this force here. So I'm going to put an equal sign here. Okay, so put an equal sign there because those two forces are equal in magnitude. Okay. So guys, let us look at this next one right here. How does this force, force 2, the y component of this force, compare to force 3? Where it's understood that if you notice here, force 3 also acts in the y direction, like this. Okay. So how does this force compare to this force? Well, remember what I said here. if we're in static equilibrium, all our forces acting in the y direction must be equal to 0. To give you guys an idea of what that would look like, let me just throw out the numbers here. Let us assume that this force here is, let us assume that this force here is positive 3 newtons. Let us assume that force 3 is negative 5 newtons. Okay. Well, if this is positive 3 newtons and that's negative 5 newtons, what does this force have to be in the y direction to balance in order to guarantee that this situation will be in static equilibrium? Well, it turns out that that force will need to be positive 2 newtons. So it will have to be positive 2 newtons. And that makes sense because positive 3 plus positive 2 gives us 5. So the 2 up forces would balance the 1 down force. So this is true of a situation in static equilibrium. All of our, if I add up all of my y components, add up all these numbers here, I will get a number that's equal to 0. So, which means that tells me that this force in the x direction, I'm sorry, this force pulling in the y direction, this positive force acting in the y direction, force 2, must be less than force 3 here, because, right, the magnitude 2 is less than the magnitude 5. So this force here, I'm going to put a less than symbol. Okay. What about the y component to force 1? How does this force compare to force 3 acting downward? Well, once again, if you notice, since all my forces in y must be add up to 0, that means if I solely focus on that component there, 3 newtons is obviously less than 5 newtons if we're solely focusing on the magnitude. So this is also less than. Okay. Well, what about the y component to force 1 plus the y component to force 2? When I add up those two forces here, how does that compare to the magnitude of force 3? Well, remember I said 3 plus 2 is equal to 5, and so this also has a magnitude of 5. So that means these two forces added together is equal to the magnitude of force 3. Okay. So that's how you do the fourth one.